So Thomas Lehman, who's our next speaker, comes from Weimar in Germany, which is where he observes his comets. And he's done a lot of work on developing methods that give us good visual equivalent magnitude estimates or comet magnitude estimates from digital data. So Thomas, over to you.
Thank you. Thank you, Nick. First of all, I'd like to thank everyone involved in organizing this great meeting. It's a great pleasure to be here with you. And thanks very much for the invitation and kind offer to give a talk. Comet photometry is an area where visual and photographic observers are contributing, amateur observers are contributing very valuable data, as we have seen by the previous talks already. Now I'm going to talk a bit about how to get there, how to get those magnitudes using my AIRTOOLS software. Let's see, I'm talking a bit about the motivation and starting my software project. I'm giving a little details about the software itself. And I talk about the data acquisition because the way how to do the observation is the basic is a basis for good photometry. And I talk a little bit about the basic image reductions and will focus mostly on the comet extraction and photometry part. I started systematic observations around 10 years ago using a DSLR camera, and at this time it was really difficult to compare visual observations and CCD observations. There was a huge gap and you could not fit data together, so I tried, essentially it was because of the small aperture, the measurement aperture you were using with the CCD data. We didn't get the whole, the large outer coma region, and so I tried to start a new project, and the main goal to extract and enhance the outer coma regions even at very low surface brightness, and then to get magnitudes reaching about 0.1 magnitude precision for at least those more condensed objects. And ideally, I would like to get some visual equivalent, and as we have seen by the previous talk, it's very important that we are able to combine both visual and CCD data and extend visual estimates to the fainter comets as well. So I presented first results in 2015, and they were quite encouraging, so I continued on that project. And to the right there's an example how it looks like now. These are just my own observations highlighted for the Comet 2017 K2 pan-stars, and I've been using 20 different instruments for these data, and as you can see in the brighter range here, the scatter can be to the level of 0.1 magnitude accuracy about. So until now I contributed about 4,500 photometric measurements to the COBS archive, and for the software I didn't want to reinvent the wheel and start everything from scratch, so I'm using software which has been well established in also in professional astronomy, like SAO Image DS9 for displaying and analyzing image data, and for example the source extractor from Emmanuel Bertin in this Astromatic software package, and a few other things. And the AIRTOOLS software, I'm essentially combining those other tools using shell functions, and just added a little bit of Python and C code. And a few years ago, just maybe 4 years ago, I started to put everything behind a graphical user interface. You get a bit easier access to those image reductions. The software runs on a Linux computer, but most observers are of course using Windows or even some Mac. So best approach is to use the software inside a virtualization environment. So you first install the free virtualization software like VirtualBox, and then you can just import a pre-built appliance, which is the AIRTOOLS software on top of a Linux operating system. You don't really have to fiddle with specific Linux tools, and you can set up those things on your Windows computer within 10 minutes or so. For detailed instruction and also for a sample project where I provide the data, you can look at the project page on github.com, and there's all the preliminary manual which covers at least the first part of the image reduction step and should help you getting started with the project. There's not very high hardware requirements. For example, I'm using a 16 megapixel color camera, and when processing a few hundred images, it's sufficient to run this on 4 CPU cores, and it's fine if you have 8 gigabyte of memory. I forgot to mention one thing on this slide, which is you should have a really fast disk, because there are a lot of I/O operations due to many temporary data which are generated during the analysis. On the right, this is my observing site located in the center of the city of Weimar in central Germany. It's not a big city, but about 70,000 people living there, so the sky is not very dark. You should use a fast scope if you want to get information about the outer coma regions to observe faint surface brightness. You should have a fast system and sufficient field of view. For observation planning, it makes no sense to take images of a comet if there are bright stars very close by, or if you have a region of a lot of galactic zeros, and then you won't be able to discriminate between the light from the comet and other sources. I really recommend the use of filters, because first of all, the effective wavelength of unfiltered images changes a lot if you use different instrumental setups, different cameras, and also if you observe it very high at low altitude, then you are affected by extinction, and so you get a lot of variation also due to atmospheric condition changes. And when I observe with the monochrome sensors remotely, I'm using always a green filter for those observations, because this might enhance somehow the gas from the coma, and also you get a much better visual equivalent brightness. A very important point is calibrations. So to the right is a plot of sky brightness. You see it's from 19 to 19.5 meg per square arc second, and also only for those nights without any moon, and also objects high on the sky. So the sky is bright, and you have to get it flat as good as possible. And with proper flat fielding procedures, I'm reaching with my rather 11-inch telescope, which is a very fast system, and using the full frame camera, I get usually to about 0.4% of deviations from an even flat field to over 90% of the field of view. And if I put some extra effort, I can get down to about 0.1% accuracy of the flat fielding. Of course, you want to get high dynamic range, so you do bracketed exposures, which is quite normal, and software does accept all common formats you get during your data acquisition. Basic image reduction, there's nothing special about this. You have the screenshot of the interface. You have just the usual steps from dark calibration, flat field, bed pixel, then registration of images, then you're stacking on stars, astrometric calibration, and you finally do a blind stacking on the moving comet by using the ephemerides. So you know the motion vector and you combine images by using that. The important point here is to do all those processing in a linear way, so you don't disturb the photometric information, and you must do all the processing the same for stacking on the stars and for stacking on the comet. Now the more interesting part is the extraction of the comet. We want to isolate the comet image from the star background, and in the first step, that's to the right, there's the second tab of the graphical user interface. You start by subtracting off the sky background, which is done by a very simple fit of a plane gradient over the field of view. I really don't recommend any sophisticated background, to apply any sophisticated background model, because you will most likely destroy the very faint outer coma regions, which you actually don't see on the images, on the stacked images at this point. The next thing is, if you want to get rid of the star trace in the stack on the comet, I use the position and brightness information from the stack on the stars and the profile of the star trail to scale this, the intensity, and then you simply subtract off the stars. And the final step is a heavy blurring and contrast enhancement to get the outer coma regions to get some contrast with respect to the background. In my software, I do not set coma regions automatically like it's done in Comfort, Nix software, for example. I prefer to do it manually, because very often the coma is asymmetric. It's not centered on the comet's head, and it's, I think, really difficult for software to decide what how to put the aperture for measuring the coma flux. Also, it's much easier to look at the image itself and to discriminate between real features which might belong to the outer rings of the coma profile, and to distinguish them from any background residual structures which might be real due to galactic zeros, or which might be artificial due to the residuals from the image reduction, essentially from flat fielding. Two examples. Here, first one is 346p. We have two images. Left is a stack on the stars. You see the moving the trail of the comet, and right is the stack on the comet, and you have the star trails here. Of course, this comet is located in an area which is almost void of stars, so you would not really need to subtract off the stars to be able to measure the flux from a comet. And to the lower left, we have the image after subtracting off the star trails. But in this case, the most important is to smooth and to stretch very much the image to make it visible, make the outer coma regions visible, and you clearly see that this coma is displayed with respect to the comet's head. Second example, 2022 W3 in a field in Cassiopeia, in constellation of Cassiopeia. So there are a lot of stars here, and you can see the very faint comet trail and a lot of stars around here. The stack centered on the comet. After subtracting off the stars, you see the comet much more clearly, but only after stretching the contrast to the very extremes, you see that the coma is quite large, at least much larger than you would expect from any of those images here. About photometry, there are two things. One is the flux measurement and the other is the calibration. Flux measurements I'm doing in these large user-defined regions of the comet region, and also from the multiple background regions. And an important point is if you compare the fluxes from measuring the stars, if you normally do stellar photometry, then you take a pretty small aperture and you measure just a few pixels wide. You choose an aperture which is just a few pixels wide, and you typically have several, maybe 20–30% of the flux outside of this measurement aperture. But with comets, if we try to measure in a very large region, you should ideally also include the flux of stars in such a large region. Of course, you cannot do a direct measurement of this for all your calibration stars, because it's a lot of other stars in the field of the aperture. But you can, from the curve of growth of the point spread function of the stars, by measuring a few larger, brighter, isolated stars, you can finally get an idea about the aperture correction you have to apply. Calibration part, to the right, there's a dialog you can choose between different catalogs, so Gaia or APES catalogs, for example. You have the choice between appropriate passband, which matches best your instrumental setup, and a color index, because I'm including a color correction term in the calibrations, and optionally also you can include extinction correction. I don't apply any correction to a standard system, because for comets I don't think it's feasible. And here's just one example of a comet 2029 Y1 Atlas, just a few weeks ago, at a pretty low altitude of 16 degrees. And we have a plot of the aperture correction and extinction, the effect of the extinction, and the color term, with calibration stars of different color indexes, and finally the photometric residuals over here. At the end of the process, you can you get ICQ records ready for submission, for example, to COBS archives. We get, as initially, I initially showed this plot of 2017 K2, and with the low scatter of data points, you can look at more detail in the light curve, and you can search for some peculiar features, like for this example, this comet has been stopping down its evolution at around 4 AU distance. And yeah, for analyzing the data of your own data, but also including the data from COBS archive, there is a light curve plotting tool provided with the software where you can plot the observed magnitude, but also the heliocentric magnitude versus date or distance. You can also plot the coma sizes, and you can highlight or hide several selected observers to study individual data. And you can also select on the different software method used, or visual or CCD observation. And you can just fit a simple magnitude model. A few examples of these, let's first look at this. A few examples of those plots. Left is the observed magnitude, and here the heliocentric magnitude for the last bright comet we have seen early this year, 2022 E3. And I have just highlighted observations from myself and another observer who's using the AIRTOOLS software. And in the more interesting plot below on the heliocentric magnitude, you see that there's clearly a deviation from the average model, which is the line over here. There's clearly an increase in activity starting just below 3 astronomical units. So you comet observers know that in this region about the water vapor starts to evaporate and might contribute a lot of additional material, a lot of additional gas in the coma, which causes the brightening, in this case by about 1 magnitude. Here the coma plots. On top the physical size, on the top the observed size of the coma, and on the bottom the physical size of the coma. You see also this comet at around 3 AU. It started to increase the coma size quite a lot. And you also see that the coma sizes are changed with the AIRTOOLS software are pretty large compared to other data. And finally, the same when comparing different methods, different software used to derive magnitudes. So there are a few other auxiliary tools like the multi-aperture photometry tool, which is much more suitable for outburst detection. If you predefine your size of aperture in physical size or in size of arc seconds, both is possible, and you can get AFRO measurements from that. There's all the tool for astrometry, and included is Aladdin Sky Atlas, which is very useful to put, first of all, for observation planning, but also to compare your own image with images from the digital sky survey. If you want to see if a feature is real or not, if it belongs to the comet, or if it is from galactic cirrus or other diffuse sky objects. And finally, there's a command line interface, so you are able, of course, to script everything if you know how to use this functions. And there are more tools like preparing pretty pictures, which is not the main aspect of the software, and it didn't get into the graphical user interface until now. But if you want, you can do it. And that's for the last slide. There's an example of an image from 2023 E2 I took about a month ago, a bit more than a month ago. It was it's the date of full moon. So that's an exposure time of 2 hours on the full moon sky. But if you have the right tool for getting really good flat fielding and to process the data, you can get a pretty flat background, which is really necessary to do the final photometry. Comet itself is not very impressive here, but just for illustration. So that's it. Thank you very much for your attention.
Thank you, Thomas. And I think that's an amazing picture at the end. Full moon from the center of a city of 70,000 people just shows what you can do with these modern instruments and really good flat fields. The software that Thomas has written is really good. Yes, it's written for Linux. Don't be scared about that, though, if you're Windows users. There's plenty of virtual machines, as Thomas has said, that make it relatively easy to use that software now. So we've got a few minutes for questions. Any questions